All right, it's 10 o'clock, so we need to get started. So a couple of good things. I did get into Moodle and I was able to create in the grade, there is a grade book in here somewhere. And in past semesters, uh, I used it successfully. Apparently, you're supposed to get a message or an email, or at least you'll be able to see it if I put grades in there. So I finished up all the chapter 3 problem sets and I put them into the grade book. Now that I don't know for a fact that you're able to see them or not, or if you received any confirmation of that. So you have to tell me, if you go into Moodle right now, can you see the grade you got on your chapter 3 problem set? All right, so if you haven't checked it, why don't you do that right now? I just want to know. If one person, if it worked for one person, it'll be good for everyone. I can see oh, okay. All right. So I guess what that means then is that when I post the grades, I have to send you an email and let you know then, or else make an announcement. All right. I wasn't sure, but at least you can see them. That's the important thing. Now, I did post the solutions as well. They're right about, oh, where are they? Here we are. So you can do is if you're not sure, like let's say you got less than 100, let's say you got a 92 and you want to know what happened. So you can download the solutions and everything's written out in great detail. And you can look at your own answers and see what happened. But if you're still not sure, and if you want more explanation or more clarification, that's fine. You can either send me an email, or if you really need a longer discussion, it's actually possible to set up a separate Zoom meeting just for one or two people. It can be done that way. So, see, like I was saying yesterday, the awkward part about this is that normally I would have to be able to hand you back a physical copy of your corrected work. And now I can't really do that. So instead, what I can do though is give you a grade. I'll give you the solutions and you can check them out. And if you're still not sure, or you have other questions, then you can let me know and then we'll discuss it separately. Okay, excellent. All right, now most of you did extremely well. There's a few people were stuck with one or two of the concepts. And so the midterm itself, if you look at it carefully, you'll see that it is kind of a stripped down version of what we've been doing. The midterm itself, I tried to avoid the excessively complicated problems, but not all of them. So, if you did well on this, and of course, I will be also finishing up the chapter 5 problems as well, probably tonight. So you'll have that one as well as you're working on the midterm. And but I mean, the midterm itself is exactly the same as what we've been doing. And the sample midterm, of course, is here as well. We've already covered that. This is a 4-part solution set. So you should have everything you need to finish the midterm, which don't forget is due on Monday the 11th. Okay, so I don't think it should take that long. It's not terribly. It was meant to be taken in an in-person setting in a class that lasts for about an hour and 45 minutes. Okay, so I'm hoping that it won't be overwhelmingly time consuming. All right. So one more thing too. Don't forget, you're also supposed to hand in the chapter 6 and 7 problem sets on Monday as well. So yeah, the work is piling up a little bit, but I mean, let's face it, this is a very intensive course. And also what I'd like to do, because we're getting into chapter 9 already, since the second midterm is only on 6 and 7, before we get too far ahead of ourselves, I would like to go over the second sample midterm on Monday as well, which is right here. Okay, so this is all of our discussion about the Poisson distribution, the binomial distribution, and the normal distribution. That's all that's in here. And so this is meant to be a good representation of what we'll be doing on the actual midterm. And so we'll go over this on Monday. And I think I'll be able to give you a week for the actual second midterm as well. But of course, we're running a little low on time. We've got wait a minute, let me look at this calendar for a second. Today's the 7th. Um, so, oh, okay. So in other words, next week will be a normal week. Um, the following week, we're only supposed to meet on the 18th and the 19th. Okay, so yeah, we're getting a little tight on time, but um, the actual final exam, then I can give it to you next week, meaning the week of the 18th, and or even that weekend. I mean, God, I could post it now if we needed to, but you should be able to hand it in. If the last day of class is the 19th, they typically give me a minimum of 3 days to hand in the grades, which would be a Friday. So there's a pretty decent chance that they'll let me hand in the grades the following Monday. And I will check into that because I'd like to give you as much time as possible to finish up the final exam too. So, so in the meantime, we're going to carry on with chapter 9 and just try to remember to have your first midterm and your problem chapter 6 and 7 problem sets ready by Monday. Okay. And also be ready to go over the second sample midterm. So next week will be a very busy week. And we'll be finishing up all the new material. And then this week we can review for the final, and then we'll be done. I mean, it's hard to imagine. It feels like we just got started, doesn't it? Kind of. I mean, you get in the beginning of a semester and it feels like, wow, this is all brand new and exciting. And then after a while, you start to get used to it and you feel like, okay, this is what we'll be doing for a while. And then all of a sudden, it's almost time to finish. So that's where we are right now. We've got, after today, only one more full week. And then the next week is only a partial week. And that's it. But on the other hand, you think about all the time you saved during the spring semester when you can take something else besides statistics. It might make your schedule a little bit smoother because, let's face it, this is a difficult course, and getting it out of the way in the Christmas break, I think, is an excellent idea. So, all right, anyway, let's get back to 9. Now 9, oh, by the way, one more thing. I did find some material that I added to chapter 9. If we go back to Moodle for a second, before it was just chapter 9. Now I've added what I call chapter 9 appendix. This is additional material that we need to cover, which I don't know, somehow it got left out. So now I've put it here as an appendix. This is just an extension of what we're already doing, except instead of means, we'll be looking at proportions. So in the meantime, let's get back to 9. What are we doing in 9? In chapter 9, we're introducing this concept of the confidence interval. Now, what exactly is a confidence interval? It's a range of values within which a parameter, as it's called, such as the population mean, standard deviation, or variance, is thought to fall. So, in other words, we essentially never know the actual value of the population mean. If we did, none of this would be necessary. Okay. In other words, the whole point of statistics is that we don't know the actual values of what's going on in the population. And so we need to use all these different techniques to estimate the actual values that we need, like the mean or the variance or the standard deviation. If we had the actual numbers, then we'd be all set. There'd be no need for statistics at all. Well, I shouldn't say that. You still might want to use techniques to help you understand what those numbers represent, but a lot of the work would be unnecessary. But here, we're assuming that we're trying to estimate the population mean. And as we've seen before, we can do that with the sample mean X bar, which is fine. But the drawback to using X bar to estimate mu is that it's only a single number. So that means that the value of X bar is heavily dependent on the particular sample that I've chosen. So it might make me uncomfortable to think that, this estimate could be fairly far off from mu if I've chosen a bad sample. So what can we do? Instead of relying on just X bar by itself to help us understand the value of mu, we can create an entire range of values within which we think that the population mean falls. Okay, so what that does is it gives us a bigger or better idea of what's going on with mu, in addition to how much uncertainty there is from one sample mean to the next. Okay, so I think we used the example of commuting to school yesterday. we saw there were two cases where we had the same mean, but very different ranges of possible values. And so the confidence intervals that we construct are designed to give us more information about the possible range of values for mu as opposed to a single number. And so that's what the purpose of this is. So you'll see this all the time. If you get into a more advanced class, you'll see these used on a regular basis. So anyway, how are these things constructed? Now, keep in mind, for this chapter, we're only focusing on the population mean, although actually in the appendix, we're also going to introduce something called the population proportion. A proportion is simply the ratio of, within a population. Let's say we're interested in the proportion of people who are retired. Well, then all that represents is the number of people who are retired divided by the size of the entire sample or population. But here, for this first part of chapter 9, we're focusing all of our attention on trying to estimate the population mean with our confidence intervals. All right. And now what's interesting here is that these confidence intervals will have a probability attached to them, which we get to choose, as it turns out, depending on how precise the information is that we need to have about this population mean. In some cases, we'll choose a very high level of probability, let's say 99%. In other cases, we may not need quite that much accuracy, and we may choose, let's say, 90%. But there's always going to be a probability associated with these confidence intervals. So, for example, if I have a 95% confidence interval, as it's called, that my population mean is between 5 and 10, then I'm basically saying that there's a 95% chance that the mean is somewhere in this range. And we call that, in the most general possible terms, an interval estimate, because it's an interval. A single value like x bar, as we saw earlier, is called a point estimate. Okay, point means a single value. Interval, of course, means a range of values. All right. Now, here's something we have to watch out for when we choose these probabilities. The wider or the higher the probability that we choose, the wider will be the interval, and the less precise will be the information that we have. Okay, so let's just think of an example of that. Again, let's go back to the idea of commuting time, just as an example. Suppose that your mean commuting time to school is 24 minutes. You want to construct a 95% confidence interval for your commuting time. Now, suppose that you end up discovering that this interval is, so that in other words, you have the probability, and let's say it turns out to be from 20 to 28. Oops. All right, hold on. Okay, so that's your 95% confidence interval. And then suppose you say, you know, that's good, but that leaves out 5% of the possibilities. What if I want to increase that to 99%? In other words, I want to be really, really sure that the population mean is somewhere in this interval. So what would end up happening, and we'll see why in a few minutes, hold on a second. If you now decide to create a 99% confidence interval, it could end up being something like this. Oops. Okay, in other words, what's going to happen here is that in order to be more confident, let me copy this into the same slide so we can see them together. So the idea here is that a 99% confidence interval means you're more certain that the mean is in that interval, but in order to be more certain, you need a wider range of possible values. Okay, so this is always going to be the case with confidence intervals. the higher the confidence that you need to have, the wider the interval has to be. Okay, so in other words, this 99% confidence interval includes the extremely rare cases where your commuting time is even longer than usual or even shorter than usual. So anytime we construct confidence intervals, the choice of that probability will determine how wide the interval is. And so for that reason, you want to be a little careful choosing that probability. And although I must say that in finance and economics, most of the time we use 95% confidence intervals. It's a standard thing because it makes sense. It's been discovered from historical experience that this works very well most of the time. But sometimes you do need different levels of confidence in your intervals. So, but when we do construct an interval, it always has a probability attached to it. All right, so with all that being said, how do we calculate these intervals? Well, we always start out with our point estimate. So if we're dealing with the population mean, this would be our X bar. And then we have some margin of error. Now, the margin of error, if you look at these very carefully, you'll see that the center of this interval is 24, which means that this interval would have been constructed by taking 24. So the interval is actually X bar plus and minus 4. Okay, you can tell because obviously this is 24 minus 4, and this is 24 plus 4, which implies that our X bar must have been 24, and that the margin of error is 4. Okay, so in other words, this is what gives us the interval. The point estimate, some estimate of the mean, plus and minus some margin of error. And that margin of error depends on several factors. That's what's really going to separate one confidence interval from another. Now, for this case, though, you can see that this, again, was 24, but look how wide the interval is. We now have X bar plus and minus 6. Let's write it like this. Okay, so in other words, in this interval, with the higher confidence level or higher probability, we have a higher margin of error. So the more confident you need to be, the higher will be the margin of error because you have to allow for more possibilities. Okay, so this includes the extremely rare cases and all the more common situations that you're more likely to run into. So if I wanted 99.9%, for example, well, let's see, what might that look like? Let's say that it would reduce it, the interval might become 16 up to 32, let's say. All right, so let me squeeze that in here. 99% could potentially be, for example, let's just sneak it up here. 99.9%. That makes it even wider. And you can see in this case, the margin of error is 8. Okay, so now, of course, we can go in the other direction too. We could choose 90% as our probability or confidence level, and that would mean the margin of error would be smaller. So in other words, if I take this now and reduce that probability to 90%, then I could end up with, let's say, 22 to 26. So now the margin of error is only 2. Oh, sorry, that's 26 plus 2. So now this implies that the margin of error is only 2. All right, so yeah, we can carry on from here, but I just want to get that out of the way up front. The idea that there's a direct relationship between these probabilities and the width of the interval, and it's all coming from this margin of error, okay? The mean never changes. It's the margin of error that's affected by this probability that we choose. So again, in general, what we're actually doing is taking what's called a point estimate and adding and subtracting a margin of error. And I started to mention yesterday that the margin of error depends on one thing, and that one thing is, do we know the population standard deviation? Okay, so obviously we either do or we don't. It's yes or no. So if the answer is yes, then we can construct our confidence interval with this following scary looking formula. All right, well, it isn't that dreadfully scary, but it's getting up there because we have a lot of new symbols here. Well, not really, not a lot of them, but here's alpha. We'll explain what that means in a minute. Alpha, the first letter in the Greek alphabet. By the way, here's a little fun side fact. This is alpha. This is beta. Guess what happens if you bring these together? And if you sort of lose this A, what do you get? There's the origin of the word alphabet. Oh my God. Who knew? All right. Well, anyway, enough of that fun stuff. Here's our, of course, population standard deviation. Okay. This is, of course, the sample size. That hasn't changed. X bar, of course, as always, is the sample mean. Now, this Z, of course, refers to the standard normal distribution. This is a standard normal variable, random variable, or what I should say is that it actually represents a specific Z score. Once we know the value of alpha, we can determine the actual value of the Z score. So in order to do this, I'm going to show you some nice shortcuts. We're going to do this in 2 different ways. We're going to do it with our tables, and then we're going to do it with our calculators. Okay, so we need to take a little detour here into the standard normal distribution. Our favorite, probably, is that our favorite? Oh, I just thought of a perfect opportunity for a poll. Okay. Why not? We have time for a poll. Okay, let's do this. This will be interesting to see. Okay. Wow. So far, binomials in the lead, but normal's catching up. Oh boy, it's going to be close. All right. Well, I guess that was that. That was an interesting little race. So far, no. More votes are coming in. No, binomial, I think, has an insurmountable lead now. You might change your mind when you see the T distribution, but so far, okay. So the popularity contest goes to the binomial distribution. Okay, that's cool. So anyway, but we do need to take a deeper look into it. Now, first, let me go get the normal tables. Our old friend positive and negative normal tables. And what we're going to do is this. Okay, so here's the normal distribution, standard normal. By the way, in each of these, this entire discussion assumes we're looking at the standard normal distribution. So basically, we're getting used to calculating normal probabilities. So if I said, for example, what's the probability that z is less than or equal to 1? You recall that there's two different ways we can get this information. We can go to our tables, okay? The table's set up to look for cumulative probabilities, which means less than or equal to. But keep in mind, this one has to be written as 1.00 to use the chart. You need the intersection of 1.0 with 0.00. And if you look at it again, you'll see right here that that's 0.8413, which is the same thing as saying 84.13% of the total area is under this curve. So the probability is 84.13%. Now, what if we wanted to work this backwards, though? What if I did this instead? What if I was interested in looking for a z-score, which I'll call just z, where the area above it is, let's say, 10%, and the area below it is therefore 90%. So whatever the z is, the probability of being greater than that is equal to 10%. So we've never done this before. Up to this point, we were given a specific z-score and we're asked for a probability. Now we're working it backwards. We're saying, here's a probability. What's the z-score that corresponds to that probability? Well, here's what we have to do. We can look in the chart for 0.9. Okay, so we're going to look in the body of this chart for the closest value we can find to 0.9. So if you look through it very carefully, you'll see right about here, this is as close as we're going to get. 0.8997 represents 1.28 standard deviations above the mean. Okay, so that z-score is 1.28 because the probability of being below that point on the curve is 90%. Okay, so let's do another one because this is going to take a while to get used to. Suppose instead I did this. I need to find the area such that, or the z-score, such that this area is 5%, which means the rest of this is 95. Okay, so let's go into the body of the table and look for the closest thing we can find to 95%. Okay. 0.95, let's see, where are we? Oh, wait a minute, look at this. We have a tie. It seems to be halfway between these two numbers, which are 1.64 and 1.65. So by convention, we will call this number 1.645, which is halfway in between them. Okay, so this z-score is 1.645. Okay, again, because it's halfway between 1.64 and 1.65. It's right smack in the middle. So this means This is the same thing as saying the probability that z is less than 1.645 is 0.95. Okay, now, as it turns out, your calculators can do this much more quickly. If you're using one of the Texas Instruments calculators, you have another option here. If you go to your second VARS button, there's a function listed there towards the top, which is called INV norm. On my calculator, it's number 3. So what you're going to do is type INV norm, which stands for the inverse normal distribution, by the way. And you're going to need to tell it 3 things. The 0.90 is what it's calling the area. And then you need to remind it that you're looking at the standard normal distribution, which, by the way, those values should already be there unless you've changed them in the past. But the 0.9, you have to change it to 0.9. Mu equals 0, sigma equals 1. The calculator does assume that that's what you mean if you don't tell it otherwise. So if you go through all those steps, what do you get? Oh my God, it's 1.28. Look how easy that is. Okay, so in other words, instead of being given a z-score and being asked for a probability like we used to do in chapter 7, now in 8.2, but for that matter, now we're working it backwards. We're being given a probability and we're asking for the corresponding z-score. Okay, so we all got that one, 1.28. Now for this one, we're going to do the same thing. Except this time, the area is 0.95. Okay, the mean is still 0. The standard deviation is still 1. And you should get, when you plug all that in, and you'll notice that it's only an approximation. What we had before was only an approximation. Okay, so what we're going to get is it's actually 1.64485. We'll round it to 1.645. Okay, so now we are used to this new idea that we can calculate probabilities. Actually, we can calculate z-scores based on probabilities just as easily as we can calculate probabilities based on z-scores. All right, why do we need this? Because this is part of this formula. Now, if you look at the z alpha over 2 is a z-score. So what does that alpha mean? Alpha determines the degree of uncertainty associated with your interval estimate. A low alpha means a high probability that the interval estimate contains your population mean or whatever you're looking for. So we're going to define 2 key terms here. 1 minus alpha is referred to as the confidence coefficient. If we multiply that by 100, it's called the confidence level. So in other words, imagine that I choose alpha to be 0.05. Then 1 minus alpha is, of course, 0.95. And 100 times that is 95%. So in other words, I choose alpha of 0.05 if I want to construct what we will call a 95% confidence interval, which means there's a 95% chance that the interval actually contains the true value of the population mean. It's never going to be perfect. Okay, you know, if we don't know what the population mean actually is, but we can get pretty close to it with these intervals. So the alpha determines the confidence interval that we're constructing. So similarly, if alpha is chosen to be 0.10, then 1 minus alpha is 0.9. And of course, that implies that 100 times 1 minus alpha is 90 or 90%, which means we're about to construct what we will call a 90% confidence interval. All right. By the way, here's a helpful hint. Most of the time, we'll choose either 90%, 95, or 99. Those are the most common ones. You can do anything you want, but those are the ones you see the most commonly used in practice. And of those three, 95% is the most common. In fact, if you look into Excel, Excel by default assumes that you mean 95% when you create a confidence interval. All right. Well, what does that have to do with this mysterious Z alpha over 2 term? All right. Well, now we can tie all this together and say, well, you know, suppose, for example, let's say alpha is, let's say, 0.05. This means that I want to construct a 95% confidence interval. Therefore, alpha over 2 is 0.025. What is the value of Z alpha over 2 then? Okay, so it's going to be used in this formula to represent this, the Z-score. Okay, so wait, hold on. Okay, there we go. All right, so that means, now let me draw a picture here so you can see what this is all about. We're going to have the following. Now remember, the formula is Z x bar plus or minus Z alpha over 2 sigma over radical n. So we actually have 2 Z-scores here. And remember, we've chosen alpha to be 0.05 and alpha over 2 is 0.025. So whatever these two numbers are, we have 2.5% of the area in this right tail and 2.5% in this left tail. So we can now look these up with our tables or the INV norm function. We have to be careful though. This one, for example, means that I've got 2.5% in the right tail. And for the entire rest of the distribution, all the way down to negative infinity, this is equal to 0.975. So if you look at the table for 975, you'll find it. Oh, here it is. It's exactly 9750. I like that. That's going to give me a z-score of 1.9, 0.06. So that means that this value is 1.96, which implies now, what about this one? Well, due to the symmetry of the normal distribution, we don't have to bother calculating it because it's just negative 1.96. Now, that's pretty convenient. So that confidence interval contains all the values that are within 1.96 standard errors of the mean. So this interior piece represents the interval that we're constructing. Okay, so the interval will actually fall in this range in here. These are the outside areas. These are the parts that get essentially left out of our interval. So in this formula, if we're constructing this interval, this would be plus and minus 1.96. These come from the data in the problem, as does this. So this part is really the only mystery. Ooh, that was complicated. Luckily enough for us, though, when you're using the standard normal distribution, there's really only 3 values that you might normally encounter. This is one of them. Okay, so in fact, I think there's a little chart in here somewhere. No, but I've got all 3 values already looked up for you. So let me just show them to you so you don't have to go through every single one of them. For 99% confidence interval, alpha is 0.01, alpha over 2 is 0.005. And if you look that up in the table, you'll discover that the correct value for Z is 2.576. Okay, you can look it up yourself if you want to, but it's already done for you. Oops, a little typo there. Okay, for the next one, now 95% we just got through doing. Not 196, okay. And now for 90%. For 90% confidence interval, your z-score will be 1.645. All right, with all those being said, the rest of it kind of falls right into place. So here it is. We're going to revisit, this is our formula, and we're going to look at some examples now. So we have a hedge fund that holds a portfolio consisting of 500 stocks. The annual rate of return among these stocks is normal. And the standard deviation, now this is intended to be a population standard deviation. I probably should have written it in there like that, but since this is the entire population, if we know that the standard deviation is 20%, that implies that this is a population standard deviation. If we have 10 stocks, and now the sample mean is 8%, we're going to now construct a confidence interval using all 3 of the confidence levels. In other words, 90, 95, just to get the practice, and 99. All right, well, let's do it. So the first thing you always want to do is calculate that so-called z-score, okay? So for 90%, we've already seen that what you're actually looking for are the z-scores such that 10% total is in the 2 tails, 5% each, and that works out to be 1.645. Now, The rest of this is just substitution then, because you know that the sample size is 10. The sample population standard deviation is 20. This is my z-score, and that's my sample mean. So it turns out that the margin of error on this side is about 0.104. And the sample mean is 0.08. So you're subtracting, this one represents 0.08. And this one is 0.08 plus 10.104. And that's where that comes from. So what they're saying here is that there's a 90% chance that the actual population mean is somewhere in this interval. We don't know what it actually is. We think it's 8%. That's our best guess, 8%, but we are allowing for the possibility that it could actually be somewhere in this range. All right, so now, if we want to change this to 95%, the only thing that will be different is this z-score, because the only thing that's actually changing is alpha. The rest of it is exactly the same. So for this next step, when we go to 95%, this 1.645 will become 1.96. The rest will stay the same. And you'll notice that with a higher z-score, it will have a higher margin of error. With a higher margin of error, the interval will become wider, which is exactly what we were talking about earlier. So let's see the exact results. So there's our 196. Now the margin of error has risen to 12.124. Previously, it was 0.104. And you can see as a result, the interval has gotten a little bit wider. Okay, let me just go get the other one for a second, just to remind you what it used to look like. So this one is 95%. This one down here is 90%. And the key difference is the margin of error, which itself is driven by the z-score. So you can imagine when we go to 99%, the margin of error will increase and the interval will get even wider. And that's exactly what's going to happen. So if you recall, when we looked that up before, the margin of error, the z-score is 2.576, which is quite a bit larger. And you plug that in and oh my God, look how big it is now. And so as a result, look how wide that interval is now. That's a big one. In fact, you see that the margin of error is actually larger than the sample mean, which means that there's a lot of uncertainty here. This one is very, very uncertain. In fact, if you look at that range, I mean, that's not a great deal of information. Suppose somebody told you that the return to the stocks is 8%, but it could be anywhere between a loss of 8% and gain of 24%. That's not a whole lot of information, is it? And you can see the reason why this is happening is because the standard deviation is so large. That means this is a very volatile stock or set of stocks whose value fluctuates a lot over time. Okay, but these are the numbers, and so whoever asks for these numbers will, do whatever they want with them. But we've created the correct margins, calculate the correct intervals, so that then it's up to somebody else to interpret them. Okay, so you know what I wanted to do, just to be really 100% clear. I like to have everything organized on one page whenever possible. It's like helpful to have a chart of everything all together. So I'm just going to copy these again. That's 95. That's 90. This is 95. So let me label these correctly. And 99%. So this way you can see that what separates them all really is this margin of error, which comes from the z-score. And you can see how the interval keeps getting wider as we try to increase the confidence level. All right. Now, all of that discussion was based on the assumption that we had knowledge of the population standard deviation. Most of the time, that actually won't be true. All right. It's kind of unusual, as a matter of fact. So when that happens, we have to rely on a brand new probability distribution, which I mentioned yesterday, I believe, is known as the t distribution. Okay, the t distribution. Now, the t distribution is similar in a lot of ways to the standard normal distribution. Okay, what really makes it different is that it's more spread out. Okay, in other words, let's see if I can give you a rough idea of what they look like. Let's say this is the normal distribution, standard normal, I should say. The mean is 0. Now the t distribution, which I'll draw, let's say with red, looks more like this. Oh, it's not perfect, but oh, that's not so bad. I cheated a little there. What I wanted it to look like is that this one is more or less, it's the same shape. It's also a bell-shaped curve. It also has a center, a mean of 0. But if you notice, there's more area in the tails. In other words, you're more likely to get an extremely large outcome and an extremely small outcome. But in exchange for that, you get less values in the middle. Okay, so that's what really makes the t different. The t distribution is more spread out, which means extreme outcomes are more likely. Than with the normal, standard normal. Okay, so in a nutshell, that's what really separates the two. So you're probably wondering, well, what's the big deal? They look very similar to each other, but yes, it can make a great deal of difference. Now, the t, unlike most of the other distributions that we've been looking at, for the most part, they were developed by mathematicians or statisticians, and they've been around for quite a long time. In fact, I think the normal distribution was invented, I believe, in the 18th century. And the Poisson and binomial came along a little bit later than that. The t distribution is a relatively recent newcomer, I guess, to the party of distributions. This was created in the early 20th century. And what was interesting about it is that it was created by a gentleman named William S. Gossett. Now, Gossett developed this distribution as in his role as the head of quality control at the Guinness Brewing Company in Dublin. Now, what exactly was he doing there? Well, what is quality control? This is where you are manufacturing a product and you want to make sure that the product is being manufactured correctly. In other words, you don't just make stuff and sell it and hope for the best. So these, obviously, Guinness is a brewery. They're making beer. And of course, beer is a very complex, making beer is a very complex process, partially because it contains yeast, which is alive. And so a lot of things can go wrong when you make beer. So the company has to make sure that the beer that they're producing is actually fine before they sell it to the public. That means a lot of testing. The problem with testing, though, is that in order to test the beer, you have to consume it and not sell it to the public. So you want to keep the testing as low as possible and yet still get the results that you're looking for. So Gossett came up with this technique for explaining or describing the means of small samples with the t distribution. Now, remember, yesterday we looked at the central limit theorem, which told us that if our samples are less than 30, and we don't know for a fact that our population is normal, we must use a different probability distribution. Well, this is the case, or this is the one that we can use when we do have that situation. Okay, in other words, if there's more uncertainty about the means of these samples that we're looking at, then we can rely on the t distribution. Because with small samples, the means are likely to be very different from each other. And so this curve represents more of a spread among the means of all these different samples. So it's a better representation of what's happening among small sample means than large sample means. And so this is why Gossett created it. Now, the interesting part is that you notice that it's not called the Gossett distribution, it's called the t distribution. In fact, sometimes it's called, let me throw this in here, just a little bit of historical interest here. The t distribution is also known as the student's t distribution. So you're probably wondering why. Why don't we just call it the Gossett distribution? Well, here's what happened. When Gossett arrived at Guinness to become the head of quality control, his immediate predecessor had been involved with industrial espionage. What does that mean? It means that the guy was selling secrets to other brewers from the Guinness Brewing Company. He was stealing the recipes, basically. So that meant that when Gossett arrived, the company decided, you know what, no more publications of research at this brewery, at least not with your own name. They were required, if they were going to publish research, it had to be anonymously. So Gossett published his results under the name student. We don't know why he chose that name, but if you look at the original paper, when it appeared in print, the name is listed as student instead of W.S. Gossett, because he wanted to make sure that he didn't get fired by the Guinness Brewing Company, because he might have, because they specifically told him not to publish any research under his own name. So that this way, the article itself doesn't have any information in it that came directly from Guinness. Okay, so nobody knows what's going on at Guinness, and yet he can still publish his paper in which he proposes this new distribution. So there you go. So he called it the t distribution in his paper, but because the paper was written under the name student, it came to be known as either the t distribution or the student's t distribution. So, we all know that it was him, and there weren't any royalties involved anyway. So, but it's just an interesting historical, story about this development, because in the other cases, typically there's no secret about it. Let's just put it that way. But what's also interesting about it here is that this was specifically meant to be used to describe small sample properties, but we do see it used in a lot of other applications. So there you go. There's your history of Guinness, not Guinness, of the tea distribution from the Guinness Brewery. Okay, so that's, you never know when you're looking at the history of math or statistics, there's always a lot of intrigue going on that we don't hear about when you're actually learning these techniques, but the history is actually quite interesting. All right, so now what we're going to do next is take a brief detour and take a look at the properties of the T distribution, and we're going to see how to calculate or come up with results from the T distribution. There's two options that we have. We have a table and we have our calculators. So before we get further into this topic of confidence intervals, we need to fully understand how this T distribution actually works. Okay, so that's what we're going to do, but it's 11 o'clock, so we're going to knock it off for a bit. And when we come back, we're going to dive into the T distribution and understand how it works before we try to apply it to our samples, to our confidence intervals. All right, so I'll see you all in about 15 minutes then. Okay. All right, so why don't we look at the properties of the t-distribution? So as I showed you in this earlier diagram, it is symmetrical about the mean, just like the standard normal. It is a bell-shaped curve, but the key difference here is that it has more area in the tails and less area near the mean. Okay, so let me get that graph back. So in other words, the t is more spread out. It is still a bell-shaped curve with a mean of 0, and it is spread out so that there's more area in the so-called tails and less area in the center. So what that tells us then is that the variance in the standard deviation of the t-distribution are higher than for the standard normal. So if you recall, the standard normal has a variance of 1 and a standard deviation of 1. So the t-distribution will have a variance which is larger than that. The question is how much larger. So now this is the unique feature of the t-distribution. We have, just like with the standard, well, actually, what I should say is with the distribution, there's actually an infinite number of normal distributions. So let me just throw that in here. Recall that there are an infinite number of normal distributions, each characterized by the value of the mean and the standard deviation. Okay, and of course the standard normal is a special case where the mean is 0 and the standard deviation is 1. Okay, now the t-distribution is characterized a little bit differently. So the t-distribution is characterized by a parameter, a single parameter, which is known as degrees of freedom. Okay, now this is something we haven't seen before. And the actual origin of this term, degrees of freedom, I'm not really sure where it originally came from. It's a very interesting concept. Basically, well, we'll get into this as we go along, but it's a single parameter which is usually determined by the sample size that we're using. Okay, now in each different application that we'll see of the t-distribution, the degrees of freedom will typically have a slightly different formula, but in each case it involves the sample size. Now, how does that work? I think I have a graph here. Yes, so what I wanted you to see here is how the degrees of freedom affects the t-distribution. All right, so let's look at this graph. Now, what does this represent? The green is the standard normal distribution, or Z. The blue is T with 5 degrees of freedom. So what we're going to do now is see what happens when we increase the degrees of freedom from 5 to 30. All right, so watch this. Remember, blue is T. So all of a sudden, if you look at it now, you can barely see the difference. This is still the Z. The green, which you can just barely see it now, is Z, or standard normal. The blue is now the T distribution. With 30 degrees of freedom. And you see that they're very, very close to each other. And by the way, from now on, we can get away with abbreviating degrees of freedom as DF. So with empirical research, we often will use 30 as the cutoff point. Anything below 30, if the degrees of freedom is below 30, the t distribution will look different than the standard normal. Once we hit 30 or so, the two of them are more or less identical to each other. So in fact, in many applications, we actually use the standard normal instead of t, as long as the sample size is at least 30. Or I should say the degrees of freedom is at least 30. But when the degrees of freedom is small, the two are different enough that we need to make sure that we're using t when we have small samples. All right, and again, you can see with the blue curve, there's more area in the tails and not so much area in the center. Now for this chapter, in all of our calculations, because we're looking at confidence intervals for the population mean, so when constructing confidence intervals for the population mean, the degrees of freedom will always be calculated as n minus 1. And of course, where n is the sample size. So it's a very simple calculation, n minus 1. So throughout this entire chapter, whenever we need to calculate a t value, the degrees of freedom is going to be calculated as n minus 1. And in fact, if you look at this chart that we're going to look at in a few minutes anyway, for the t distribution, if you notice across the top, we have areas or probabilities. Over on this left-hand side, this first column, if you look at this label or the header, you'll see that it's df, which of course means degrees of freedom. So in order to look up these values, you need to know the area or probability, and you need to know the degrees of freedom. Now, another quirky thing about this chart is that this is actually doing the reverse of what we did with the normal table. With the normal table, we were given a z-score and we're looking for a probability. Here it's the other way around. We've got a probability and we're looking for a t-value or t-score. Okay, it's done this way on purpose, but we can also find this information with our calculators, as we'll see in a few minutes. All right, now, here's a couple of important details too. What we're going to do now is look at the moments of the t distribution. And we're going to introduce a new concept here. I guess I left it out. Okay, hold on. Note. For the t distribution, we will represent the degrees of freedom with the Greek letter. And so it looks kind of like a fancy V. And this fancy V is the Greek letter nu. Okay, so whenever you see that fancy Greek letter nu, the fancy V, that represents the degrees of freedom. So like I said in this chapter, what you'll see is that nu will always equal n minus 1. In other chapters, it'll equal something different for the most part. Okay, in other words, every application of the t distribution, the degrees of freedom are calculated in a slightly different way. So for this, what we're doing here, the degrees of freedom is simply equal to n minus 1. So it's pretty straightforward. All right, so then with that being said, we can now define the moments. All right, so remember, every probability distribution has a unique set of formulas for calculating the moments. So we've already seen that the center or mean of this t distribution is 0. So that one is pretty self-explanatory. The mean or expected value is simply 0. The variance, though, equals nu over nu minus 2. Okay, this is this is the font that comes with the PowerPoint. It's supposed to be a new. It's hard to see the difference between this and the V, but this is the letter nu, and it represents the degrees of freedom. So therefore, the variance is defined to have a value of nu over nu minus 2. Therefore, of course, the standard deviation is the square root of nu over nu minus 2. Now, by the way, this can help us explain why the t-distribution gets closer and closer to the standard normal when we have a large number of degrees of freedom. So for example, let's go back to those two graphs that we had before. And let's look at this first case. What's happening, you know that for the standard normal, the variance is equal to 1, as is the standard deviation. Now here with the t, in this case, the variance of the t-distribution here is going to equal 5 over 5 minus 3, which is 1.67. So in other words, the variance of the t-distribution is 67% larger than the variance of the standard normal. And that's why the curve stretches out so far, okay, because it has a much larger variance. And of course, the standard deviation is the square root of that, whatever that is. The square root of 1.67 is approximately 1.29. So the standard deviation is about 29% higher than it is for the standard normal distribution. But when we jump ahead to the case with 30 degrees of freedom, look what happens. Okay, so now for the t-distribution, the variance is nu over nu minus 2. (30 over 28, which is approximately 1.07. And of course, the standard deviation is approximately then 1.035. So you can see now with so many degrees of freedom, the t-distribution's variance and standard deviation are much, much closer to the standard normal than when we only had the 5 degrees of freedom. So this is why the curves are getting so close to each other, because as we get more and more degrees of freedom, in other words, larger samples, the two distributions become very, very close to each other. Okay, so we now know the moments of the t-distribution, just like all the other ones that we've learned. So what do we do with them? How do we calculate values from this table? Well, here's a good example. Suppose that I'm looking for the following information. Let me draw a picture of the t-curve. And I'm looking for the t statistic, or t-score, we could call it, where the area in the right tail is 5%, and we have, let's say, 9 degrees of freedom. Look at the table, and this is part of it. At the intersection of these two, you'll see a value of 1.833. And that means that the t distribution, this represents 1.833 standard deviations above the mean. So under the t distribution, this occurs at this point. So in other words, 5% of the tail, the right 5% tail, starts 1.833 standard deviations above the mean. Okay. So then of course the full table has all of this information as well, but you can also squeeze this out of your calculator. And if you do, so here's what you have to do to find the same information on your calculator. You go to second VARS, and what you're looking for is INVT. And you notice it's just like in the previous chapter, we're looking at INV norm for the standard normal. This is the inverse of the t distribution. Now, when you ask for that, it needs two things. It needs an area, and it needs the degrees of freedom. Now, here's the quirky part, though. When you tell it what area you're looking for, don't give it 0.05, give it 0.95, because that's everything to the left of that point. So remember, this in this calculator, the standard normal and the t functions are all based on less than or equal to probabilities. And then of course you have to specify the degrees of freedom to be 9. And then you hit enter, of course, and it comes up with 1.833. Okay. Now, by the way, if you had put 0.05 in here instead of 0.95, the only thing that would have happened is because of the symmetry of the t distribution, you would have simply gotten negative 1.833. So it wouldn't have been the end of the world, but you would have looked at it and said, why is it negative? Okay. So in other words, if you were looking at 0.05, you're looking at the left tail, but because of the symmetry of the distribution, it would simply be negative 1.833. But here we want the positive version, so therefore you will put in 0.95. Now that's going to come in very handy when we try to construct confidence intervals using the t distribution. Because, now remember, this is the case where sigma is unknown. So that means we have to make a couple of changes. First of all, we use the sample standard deviation. And now look at this t. Now remember before we had z alpha over 2. The alpha over 2 is still here. That represents an area under the curve. This n minus 1 is there to remind us that the degrees of freedom is n minus 1. And of course, n is the sample size. And naturally enough, this is the sample mean. So the challenge, just like before, is looking up this value as part, and of course, the whole right-hand expression, this hasn't changed. This could be thought of as our margin of error. So this t can be thought of as a t-score. Sometimes it is called a critical value. Okay, so this is what we're going to do to construct our confidence intervals. All right, let's do one. We have a university with 10,000 students whose GPAs are normal. A sample of 10 students is chosen. The sample mean GPA is 3.10. The sample standard deviation is 0.25. So your first instinct, when you see this normal assumption here, you might say, well, why don't we use the Z distribution? Because using S introduces uncertainty about the spread of the values. And so even if we know that the population is normal, if we don't have sigma, we have to use the T distribution. Okay, because this number itself, S, is itself subject to uncertainty, whereas remember, sigma is a constant. If we have that value, we're good. But if we don't, there's two sources of uncertainty here, X bar and S. Therefore, we must use the T distribution. So we're going to use this information to come up with confidence intervals using 3 confidence levels. And you know which ones they are: 90, 95, and 99. So in the first case, now these we can get out of the table like we just did, or we can go to our calculators. Okay, so here, what we're looking for is this. Now, you notice the total area is 90%. It's a 90% confidence interval, which means alpha is 10%. When we split it in half, we have 5% in either tail. So once again, we can go to our table. Now, when you go to the table, you're not going to look for 0.05, you're looking for 0.95. So let's go find one of those tables. All right, so which one do we want? We want this one that I've conveniently already highlighted. Let me just erase that real fast. And this time, because the sample size is 10, the degrees of freedom is 9. So yes, we've already looked this one up. 9 degrees of freedom combined with, this is our right tail area, and these are the 2 total tail area. That's going to act as our T-score or critical value. Okay, now when that's done, the rest is easy because we're just plugging in the numbers that we have. Okay, so in other words, we have a sample mean of 3.10. We have our T-score. We have S is 0.25. 0.10, 10 is a sample size. And of course, all of this is our margin of error. And when you throw all that together, you get an interval of this. And of course, again, this is our margin of error. Now, if we do this again with a different level of confidence, this margin of error will be different. Okay, if we jump from 90 to 95%, which is what we're about to do, the margin of error will get bigger. All right, so this is saying, now you notice how close these are to each other. Unlike our previous examples, when the range was really wide, but that's because the standard deviation is really small compared to the sample mean. So this is a pretty tight little interval. Compared to, remember before, the numbers were really all over the place, and that's ultimately determined by that standard deviation. All right, so for the next one, for 95%, the only thing we have to do is look up that t-value again in our chart. So we're going to stay in the same row, but we're going to switch columns. In fact, what we're going to do is move to the next column to the right, because We're looking for 95% confidence, which means that the two tails have a total area of 5% or 2.5 in each tail. Within equal, yeah, this doesn't change. So if you look in this column, and you can tell this is the right tail area. This is the total area. So we now have a t-score of 2.262. Now, one thing I forgot to mention, I just realized it this second. Let's go back to the previous example. If you notice, the t-score here was 1.833. If this had been the standard normal distribution, you recall from earlier, this would have been 1.645. Whenever we do look up numbers in the t-table, they're always going to be larger than the corresponding value for the standard normal. And that's because of the higher level of variation from one sample to the next. Okay. Now, the other thing that I realized I forgot to do is just remind you, if you want to look up this number on your calculator, it's INVT, the area would be 0.95, and the degrees of freedom would be 9. For this case, while we looked it up in the table, you could also have done it this way, INVT of 0.975 and 9. And remember what that represents. That's the area below T. All right, so if you want to check that out, go back to your calculator and change it to 2.5% with 9 degrees of freedom, and it should come up with approximately 2.262. Okay. Now, we plug that in, and you'll see, because these are staying the same, the margin of error is going to go up. Okay, before it was about 1449, now it's 17,788, and so as a result, the interval will be that much wider. All right, so this is our interval for 95%. And the last one, of course, was 90. Now, we saved the best for last, I guess, 99%. So now the tail areas are each 0.5%. So they're way, way out here. We have a total of 1% split up between the two tails, which means each one contains 0.5%. So when you look in the table, what are we looking for? We're going to switch over to this column. 0.5% in the right tail, 1% total, brings us a t-score of 3.25. Okay, so remember, 5%, 0.5% in each tail, or 1% total, which is what this means. Oh, that's better. And that gives us 3.25. And a reminder, with the z-score, this would have been 2.576. So you can see it's quite different, isn't it? All right. Or you can go to your calculator and do INVT, make it 995 and 9, because everything below this point has a total area of 0.995. Okay. All right. So we plug that in just like we've been doing all along. And we have our margin of error. Which will be larger again than the previous two cases. In fact, it's all the way up to, wow, 0.2569. So the interval is getting a bit wider, but it's still, compared to what we've seen before, it's not that big. But the bottom line is that each time we increase that confidence level, we're going to increase the t-score, which means the margin of error goes up, which in turn means the interval gets wider. Okay. So, in fact, just like before, I think I'll summarize them for you on one last slide. So for the first case, I'll take all of this, I guess. Oops. Oh, that's convenient. Okay, now we'll do another one. Okay, and then, oh, one more. Just so you can see them all together in one place. And then for 99, we have these numbers. And that's 99. Okay, so it should be clear that as we keep increasing the confidence level, the margin of error keeps going up. And so therefore does the width of the interval. And of course, the logic is that if I want to be more confident, I have to include a wider range of values. Okay, so, and again, also, these are the three most common choices that you're most likely to run into. Not that it's impossible to do any of the others, it's just not nearly as common. These seem to be the ones that make the most sense. All right, well, that was cool. Now, all of that discussion centered around calculating confidence intervals for the population mean. So what we are going to do next, not right now, we don't want to start something new right now because it's like 11:53, but what's coming up next is we're going to introduce a new parameter, which is called the population proportion, which represents the ratio of people in a population that have a certain characteristic to the overall population. Like the proportion of people who are, let's say, left-handed could be, let's say, 10%, that kind of thing. So there's a proportion in the population as a whole. And of course, we almost never observe the entire population. So we would like to not only calculate what we will call a sample proportion, but we'll also be able to calculate confidence intervals for that proportion. Okay, this is awfully important for certain types of applications. Like, let's say a town needs to know what proportion of families have children so they can plan ahead for how many schools to build or how big to build the school that they're building, things like that. So it's, the proportion in many cases can be just as important as the mean. So we'll have to save that, sadly enough, for next week. Now, remember, next Monday, our plan is to go over the sample midterm number 2, which is exclusively in chapters 6 and 7, which means our discussions about the binomial, the Poisson, and the normal distribution. So that will come next. And when that's done, we'll get back to this material. Okay, in the meantime, you'll be providing me, I hope, by Monday with your first midterm, and I have already received some of them, your chapter 6 problem set and your chapter 7 problem set. So yeah, it's getting a little busy here, but they're not so long that that should be a problem, because you do have 3 more days to do that. So, all right. So if there's no last minute questions, I guess we'll knock it off, and I'll see you all again on Monday.
I do have one question.
Okay, go ahead.
So I kind of got lost with getting the z-score in the margin of error.
Oh, okay. Well, we'll go over those again when I go back to this on Tuesday, I guess. We'll start all over again, basically. I'll go through the whole thing one more time, because I know there's a lot going on.
All right, great. Thank you so much.
Yeah, so I'm going to post these notes today, so you can reread them if you need to. You can watch the video, but I will definitely take a step back and review all of this one more time, because I know we went through it fairly quickly. So yes, I know that that is a very complicated topic. So we'll revisit all of this on Tuesday.
All right, great. Thank you so much. Have a good one.
All right, bye. Okay, you too. Bye.